additional replicas on the on any of the randomly selected recs. So if the replication factor is more than 3. And whenever we have to read it, the distance is given a priority. So when I request the name node, I want to read some data, name node would return me the node which is nearest to me from where I can read it to reduce the network bandwidth and the network cost. Uh, Large SDFS, so this all things we have already discussed yesterday. Large replication factor, failure, fault tolerance, all of these things we discussed yesterday. Any questions anyone has on this slide? Okay, so then we discuss our name node. And so name node contains all your metadata we discussed yesterday again, and it's just the metadata which is stored on the name node, nothing else. And the real data is stored on the data nodes. So this slide talks about the name node only. It contains, when I say metadata, so it contains a list of files which align my cluster, list of blocks for each file, list of data nodes for each block, the attributes, the transaction logs, like when was the file created, deleted, and things like that. So it's all the metadata of the data which is lying in the cluster. And name node has only that thing, nothing else. Okay, so someone raised a question yesterday, I think, secondary regarding something related to secondary name node. I don't recall the exact question, but this slide would answer his or her question. So there's something called HA availability in the Yarn 2.x architecture, that is Hadoop 2. So whenever I say Hadoop 2.x, that's basically Yarn architecture, which we'll be discussing up in our later on classes. This whole PPT talks about Hadoop 1.x architecture only, and the reason is once you understand the 1.x architecture, then it will be very easy for you to relate it to 2.x architecture. That is what we call Yarn. So in all these slides, I'll be talking about 1.x architecture only, but only this slide is talking about 2.x architecture because this question is normally popped up in this class. What happens if the name node goes down? So that's the reason I've explicitly added this slide on the 1.x basics only and not into 2.x. So HA cluster is a property of Hadoop 2.x where, so what was the problem with this 1.x architecture was if the name node goes down, the secondary name node although has a backup of name node, but that has to be manually made up by the Hadoop administrator. And if something has to be done manually, you can think of there would be some delays and there could be some data loss also in some rare scenarios, and there's a manual intervention, of course. So with 2.x architecture, there's something called HA availability, that is high availability. So in that case, what happens up is, although there is something similar to secondary name node, but that is not called secondary name node. That is called a standby node. So there are two name nodes. One is always in an active state, and another one is in a standby state. Both are called name nodes only. One name node will always be in active state. Another one would be in a standby state. The active node is responsible for all clients operation in the cluster. That is when client requests for write or read operations or anything related to that, the active name node will be taking care or doing all those activities. In the order of, so basically what happens up is there are backend daemon threads which are running up, and the active node keeps on dumping the things to those daemon threads, what we call general nodes, and secondary name node keep on listening or reading from that. So it by the virtue of that, it maintains its state similar to what is there in the name node. And whenever any modification happens related to namespace or anything that are logged up into your daemon threads, what we call general nodes, and secondary name node keeps on, or a standby node keeps on reading them. And whenever your name node goes down, um, at that time, the standby node ensures that it has read all the logs which are logged into the general nodes or the daemon threads which are running at the back end, and then only it will make itself up and this all this coordination is done with the help of Zookeeper. Other than that, the data nodes also keep on sending their signals, what is their state, so that name node knows if some data node is down and things like that. And if some data node is down, it's name node responsibility to replicate the data which was lying in that data node to some other data nodes. So say if mm, uh, block X was lying in data node 1 and data node 1 got down, so in that case name node will at the back end will communicate to some other data nodes XYZ where the block copy of block 1 is lying, and will give him a signal that please copy this block to so and so data node. So by such a fashion, name node maintains the replication factor 3 inside the cluster if something goes down. So in how that can be maintained is these data nodes keep on sending heartbeat signals to the name node. So by the virtue of that, game node knows that the data nodes are alive. If some data node does not send up heartbeat signal to the name node in the predefined frequency, name node safely assumes that data node is down, and in such a scenario, it will do a replication of the data which is lying on that data node, and there will be no process which will be triggered on that data node also. So in the case of high availability cluster, that is 2.s architecture, these data nodes not only send a signal to the name node, but they also keep on sending their signals to the secondary name node. And by virtue of that, the standby node knows that which data nodes, what is the state of data nodes, and when it has to go up, there is least activity which should be done by that secondary name node, or what is called standby node, and that could be made up at very, very, very less frequency of time. Does that make sense to everyone? Any questions on this slide? So in short, what I said is in 2.s architecture, to achieve the high availability, we have two nodes. One is called active node, and second one is called standby node. Both are your name nodes only, but at a time only one node is in active state, other would be in a standby state only. So active standby keeps on reading the changes which are logged by the active node in the backend daemon threads, and data nodes also keep on sending their signals to both the nodes. So Puneet has a question. Secondary name node and the standby are same. Puneet, secondary name node is the name which is given in Hadoop 1.x architecture. There's nothing called secondary name node in Hadoop 2.x architecture or Yarn. We'll be looking into Yarn in our next classes, but there's nothing called secondary name node in 2.x architecture. So the previous slide which I showed you was Hadoop 1.x architecture. In 2.x architecture, that node is called standby node. Does that make sense?
Yeah, fine. I'm unable to type actually.
Oh, sure. Okay.
Yeah,
So, okay, I assume no other questions. Yeah, definitely we can transition from 1.x to 2.x, but nah, there are a lot of admin related things which you have to take care while doing that. But definitely you can do a transition from 1.x to 2.x on your live clusters, on your live production clusters. Okay, so data node. So as I was keep on saying, data nodes are your nodes which has your real data. So they store your real data, and they are on metadata of the blocks, which blocks are lying in the data nodes. And these data nodes keep, as I said in the previous slide, these data nodes keep on sending the heartbeat signals to your name node, so that name node knows that the data node is alive, and by virtue of that, name node maintains the replication factor across the cluster. Also have all the metadata about your data. So in this slide, I'll be adding two more things or two more complexity to the architecture which we were discussing till now. So till now we looked at something, there's something called name node, there's something called data nodes. and there's something called secondary name node or standby nodes. So that was a physical in terms of physical architecture of the system. Now what is running inside the cluster, how the real processing happens in the cluster. So let's look at that part of the cluster, the architecture of the things. So in this slide, you can see that I've added two more things. One is called job tracker and one is called task tracker. And you can also see the job tracker is lying or running on the node called name node, and the task trackers are running on the nodes called data nodes. So although in a smaller cluster, or again it's your wish, you might be running a job tracker on a name node, but you can run a job tracker or any other node which is equivalent to your name node. By what I mean by equivalent, that node should not be of your commodity hardware kind of thing. That should be your kind of your Ferrari of your system. That should have good infrastructure and good resources, so you can run the job tracker on that node also. But in a smaller clusters, you might be running a job tracker on the name node only, and that's the reason this is displayed on the name node only. And there's something called task trackers, which so job tracker and task trackers are the processes which run on your machines. So job tracker is a single instance which is running in your whole cluster. I'll again repeat, job tracker is a single instance which is running on a cluster, and task tracker is a single instance which is running on our data node. So if there are 10 data nodes in the cluster, there are 10 individual task trackers running on individual data nodes. So there are two things, job tracker and task tracker. And job tracker runs on your name node or a similar infrastructure. Task tracker runs on your data node, and only a single instance of a task tracker runs on a data node, and similarly a single instance of a job tracker in the whole cluster. How they use is what they do, we'll be looking in the next slides. So this job tracker is your, as the name itself signifies, really maintain your whole jobs in the cluster. So when I as a user submit some job, that job really goes to your job tracker, and then it's a responsibility of job tracker to track your whole life cycle of the job till it's not finished. And how that is tracked, the real logic, or the logic which need to be ran on the data, is transferred to your task tracker by job tracker. Task tracker really run those logic on the corresponding data node, and job tracker keep on communicating to your task trackers, and when the task tracker work is done, they just communicate back to job tracker that the work is done, and the job tracker again communicate back to the client. How that is done, we'll look into the next few slides. I, as a user, submit a job. Job is submitted to your job submitter, that gets an ID from your job tracker, what we looked in the previous slide. This is a unique job ID by which you can track your job in the cluster. Okay. So in this slide, I'll be talking about splits, but for a time being, just assume a split is equivalent to your block. But there's little difference between a split and block. We'll be discussing that part in some time. For a time being, just assume and understand split is equivalent to your block. The job, we just compute what are the splits. Just a sec. So we just compute what are the splits, and we copy the resources which are required to run our job. So this is a logic which is required to run our job is placed into DFS. By DFS, I mean to say SDFS, that are distributed file system. So I got a job ID, and I've placed the logic which need to be ran on the data into distributed file system. And I call submit job on the job tracker. What happens after that is I've submitted the job, and the job is placed into the job queue of the job tracker. Job tracker reads your logic which you have copied into your file system, that is SDFS file system, and creates map and reduce, which is the real thing which or program which basically do your data processing. So the logic which I have mapped in the DFS, that contains the mapper logic and the reducer logic. What is mapper, what is reducer, don't worry about that part right now. Just keep in your mind there's something called mapper and something called reducer. We'll talk about them in very much detail. So it creates your instances of map and reduce, And the number of mappers is always equivalent to a number of splits, or for a time being, you just assume it's equivalent to a number of blocks. And this task tracker keep on sending heartbeat signals to a job tracker. As the data nodes keep on sending heartbeat signals to name node, these task trackers also keep on sending heartbeat signals to a job tracker. Job tracker picks the job from the job queue which it has placed in the previous slide and assigns those tasks to the task tracker. Task tracker, now the job tracker is down, task tracker is up, please mind. Task tracker, the task which is assigned to task tracker, that task tracker reads the logic which need to be triggered on the data from the distributed file system and initiate a new JVM. And in that JVM, that logic runs up to do the data processing. And once the data is processed, it's communicated to the job tracker, and that's how job tracker maintains the whole life cycle of the job. And task tracker just run the individual instance of mapper or reducer on the local data node. I'll repeat the whole process once again, but any questions before I repeat this whole process once again? No questions from anyone? Was it clear? Shall I repeat or not?
No, please repeat. No, because it was too fast, like the entire
Yes.
process, if you can.
That's the reason I told I'll repeat it again, because first time in one go it's difficult to digest. Yes. So Puneet has a question. Padme, I'll just repeat it. Puneet has a question. So when is the real? So when the so Puneet, that's the beauty of the cluster. You don't really flow the data in the cluster. If I have to flow the data in the cluster, I am doing a data transfer over the network, and if I'm doing a data transfer over the network, I am again stuck with so if I have to process say 1 petabyte of data, and if I have to transfer that 1 petabytes of data on the network, I my whole time is wasted in the data transfer only. So if you remember the previous slide, what I talked about is we read the data locally, we do the data processing locally, and just return the the summarized data, or summarized logic or the output which you want on the data, and that output is only transferred over the network. Although there is some more data transfer which happens in the real MapReduce phase, so we'll talk about that in the MapReduce cycle. But it's just the logic which flows in the cluster, and the logic size is always few MBs or few bytes, so that reduces the data flow in the cluster. If I have to flow whole petabytes of data, then I'm all down with the network bandwidth and network choking and all those things. And again, I'll be in the same loop to of if I have to copy the data to single node and do the processing over there, then I am not using the power of horizontal scaling. Okay, so how the first time data goes it. Okay, so first time the data is copied when we when we do a write signal. So when I say write to my name node, as a client, say I have to write 5 petabytes of data into the cluster. I'll just give a write signal to name node. Name node will return where that data need to be copied in for each block of the data. I'll be copying that data in the nodes. So that data is now already exists in the cluster. I'm talking about how that processing happens on the cluster. How the write anatomy works up, I'll talk about that part also in detail in the next slides over here. But in the slide, I'm talking about how the data processing happens up. So once, if your data is there in the cluster, how that processing of the data happens in the cluster. So Chris has a caution, can multiple tasks process the same data? Definitely, Chris, multiple tasks. Padmini, you can have your type of question over here. So Chris, definitely multiple tasks can process the same data. Two users can always query the same data. In that case, there will be two job instances which would be running up. Job tracker knows which task tracker is idle, which data node has bandwidth to trigger that. So basically, which data node has a bandwidth to run more JVM instances, because task tracker keep on sending heartbeat signals to These task trackers keep on sending heartbeat signals to the job tracker. When they send heartbeat signals to the job tracker, they not only send the heartbeat signals, they also send what is the status of the current jobs which they are running and how many jobs they are running and things like that. So when job tracker knows how many jobs they are running, what is the state of current job which is being ran in the task tracker, job tracker knows how much CPU, how much RAM is still available on this task tracker to run new process. So if the same data need to be processed by two different jobs, definitely there is more than one copy available. So in that case, job tracker intelligently assigns the different tasks or to different task trackers, and the data is processed on a separate machines so that there is no write logs, oh sorry, read logs. I'll again repeat this whole flow, add few more complexities and few more things, and then again you can ask your questions. So by the time you can again you can type your questions over here. I'll read them, but before that I'll again repeat the whole flow and add few more complexities. So I as a user submit the job. The job is submitted or is submitted to task tracker. And task tracker is the main entity is submitted to job tracker, and the job tracker is the main entity which manages the whole life cycle of the job. So all the bookkeeping activities related to job are done by the job tracker only. The task tracker just run the logic in the corresponding. Everyone understand what is JVM? Is there anyone who does not knows what is JVM? Okay, so Padmani says no. Okay, so Padmani, any of the Java process basically runs in a Java virtual machine. So JVM is a short form of Java virtual machine. So any Java instance or any Java process basically requires a JVM instance to run over there. So as map and reduce are written in Java, so they require Java instance or JVM instance to run. So when I'm saying JVM, that JVM instance is triggered and the map and reduce logic is basically spooled in that instance. So JVM is an instance, Java virtual machine instance which triggers on basically where your real map and reduce code is basically ran. So I as a user submit the job. Job is submitted to the job tracker, and we compute the number of input splits on the data. So a split is equivalent to a block. For timing, just assume that part. I'll slowly and slowly introduce the complexities. And once the job is submitted, I have got the job ID. By that job ID, you can always track the whole life cycle of the job. That job is placed in the queue of the job tracker, and whenever job tracker knows that some data nodes are idle or has a bandwidth to trigger new jobs, the job tracker picks those jobs from the queue and assigns the job to the task tracker, which can run the job, or which can run the task of a job basically. So if you can recall now, my whole file is divided into 5 blocks. If you recall my previous example, my file was divided into 5 blocks. So in that case, when I have to process that file, the job tracker would be communicating to 5 task trackers to really do a whole processing on that file. So in that case, job tracker will be communicating to 5 different data nodes and the task tracker which are running on those data nodes to do the whole processing on the file. And how that is done with the help of map and reduce. So when I'm saying the splits for a timing, assume the splits are blocks only. So though that's the reason I'm saying number of splits is equals to number of maps. So those maps are triggered on the data nodes where your file blocks are lying up, and on those blocks that logic runs up, and that logic is run with the help of task tracker which is running on the data node. And these task trackers keep on sending heartbeat signals to a job tracker, and by the virtue of these heartbeat signals, job tracker knows what is the state of the task taker? If task taker is down while doing some processing, the heartbeat signal would not be sent by the job tracker to sorry, by the task taker to the job tracker, and in that case job tracker knows that the task taker is down and no further request would be given to that data node where the task taker was running up, and the processes which that task taker was running, which has failed to send the heartbeat signal in the predefined frequency, those task would be assigned to some other data nodes or the task trackers where that block replicas are lying, which were being processed by this task tracker. And always a new instance of JVM is triggered for all the logic or all either map or reduce code which need to be triggered on the task tracker. And these task tracker and job tracker itself themselves also run in a JVM instance. Now, before I ask few questions to make it clear to all of you, uh, do you have any questions? Do you want me to repeat again, or does it make sense now? Or was it complex? Okay, so Chris has a question. How does job tracker communicate with the task tracker? It's through queries. No, 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 no. It does not communicate through queries. These are the signals. So there are different communication mechanism. Some people communicate with TCP over TCP. Some communicate TCP over HTTP. Some at some places is so there are different protocols used at the backend to do all this communication. I'll talk about what are the different protocols used at different layers, at different communications. So when data node communicate to name node, again they communicate on different protocol. When job tracker communicate to task tracker, again they communicate on different protocols. The RPCs, HTTP over TCP. I'll tell you all of them. So they communicate on different protocols. Any other questions before I ask few more questions? Okay, so I said that the task tracker and the job tracker runs are a process, and they themselves also run as JVM. But here you can see the task tracker always creates a new JVM instance for the logic or the mapper or reducer code which has to process or basically run. Can anyone answer why job task tracker creates a new JVM instance for your process to run rather than running that logic itself in the same JVM on which task tracker is running up? I'll again repeat my question. Task trackers and job tracker runs in JVM instance only because they are again Java codes. But when I have to run a mapper or reducer code, a new JVM instance is initiated from the task tracker, and that map or reduce code is ran in that JVM instance rather than the same JVM instance on which task tracker is running up. Can anyone think of what could be the reason behind that? Yes, Chris, a new JVM means new process which is on threads, and there's an overhead to create a new JVM. Why that overhead is really required by the task tracker? Why it can't run the logic in the same JVM? So Padmini, again for you, I'll repeat. JVM is basically kind of Java instance on which you run the Java code in very simple term. So task tracker is a Java code, job tracker is a Java code, and the map and reduce code which do your data processing are again Java codes. So they require some Java virtual machine instance where they can run up. That is the environment on which Java code can basically run up. So you can run n number of Java codes in the same JVM. But over here, that's not done. Task tracker create new JVM or Java virtual machine instances on the data node to run mapper or reducer codes. Any guesses from anyone? Why really new JVM instances are required from the task tracker, and it cannot trigger it in the same JVM where it's running up? No guesses from anyone? Okay. Let me answer my question. So say a task tracker is running up a map reduce code or a mapper code or a reducer code, and there are some issues while running that mapper code, and that mapper code fails up, and due to that, the JVM instance fails up. So if the JVM instance fails up, the whole task tracker is down and the whole data node cannot do anything. So to reduce such kind of risk, task tracker always initiate a new JVM to trigger your logic. Although there is an overhead to create a JVM instance to run your logic, but that overhead is always good as compared to the whole task tracker going down. And at the back end, job tracker also takes care of a few other things. So say the job trackers, so say there is on this, this is a data node one, and this is a task tracker which is running on this data node. And say there are few blocks of a file, say block one and block 9 of a file F, which I'm doing processing. And similarly, there are other blocks which are lying across data nodes, and the task trackers are doing processing over there for this file where I've submitted the logic to run up. Now, when this task tracker send the heartbeat signal, as I said previously, it also sends where it is where its processes are. So how much percent the mapper has run for this block one, how much percent the mapper has run for block 9, and so on. So in that case, if say this JVM instance was running for block 9 and this failed due to different reason, it will send a signal to job tracker that it has the JVM for block 9 has failed. And what job tracker will do is will just figure out from the name node where another copies of block 9 are lying, and will assign a task to that task tracker to run for block 9. And next time, whensoever any request comes up for that file need to be processed up, job tracker will mind that the block 9 processing failed on this task tracker, that is data node 1, and job tracker will not give to data node 1 until unless it has no other options. It will try to give that block 9 processing to some other node where the copies of block 9 are lying. So Puneet has a question. Sorry, slowly and slowly read one by one. What the task tracker Java code what the task tracker Java code does perform. So Puneet, task tracker is just doing the task. So task tracker Java code is doing step one, listening to the tasks which are assigned from the job tracker to the task tracker. Step two, initiate a new JVM instance and run the logic which is read from the first read the logic from the distributed file system, run that logic in the JVM instance which it is initiated, and keep on pooling these JVM instance to figure out what is the state of the process which is running in this JVM, and send that state to the job tracker. So this is the Java, this is what is done by the Java code, which is basically displayed as a task tracker in this slide. Does that make sense? Chris has a question. So there is one task tracker that has multiple tasks, each task assigned to us data block. One task tracker that has multiple tasks. No. Chris, let me repeat again. There's always one task tracker running on the data node. Okay. Just give me a minute. Just give me a minute. So this is my cluster. Name node, data node, data node, data node, data node, data node. So say 1, 2, 3, 4, 5 data nodes in the cluster. And this is a name node. So your job tracker would be running on the name node only. So this is your name node. Job tracker is running on the name node only. And these are your data nodes. Let's say color green. And there is a single instance of task tracker running on a data node. So there's one task tracker running over there, one task tracker over here, one task tracker over here, one task tracker over here, one task tracker over here. So let's again give them the JVM curve. Now I as a user came and so let's say before that there's a file F which is lying in my cluster, and that file is say employees file, employee data, employee data. So file size say 100 MB or say 200 MBs, 200 MB, total 200 MBs. So approximately it would be is equals to 200 divided by 64. So approximately 4 blocks it will be distributed to. So let's say block 1 is lying over here, block 2 is lying over here, block 4 is lying over here, and block 3 is lying over here. And this is your data node. Sorry. This is your data node 1. This is your data node 2. This is your data node 3, data node 4, and data node 5. And the block 1 copy is lying over say, okay, let's put the copies also. So here block 1, say block 3, and say block okay, 2 only. And here say block 2 and say block 1, and here say block 2, block 1, and say block 4. Here say block 1, 1 copy, 2 copy, 3 copy are done. Block 3 only 1 copy is still, and block 2, okay, and block 4 3 copies now, and block 2 3 copies, block 1 1 copy. Okay, so this is my file in the cluster. All the blocks replicate thrice in the 5 data nodes, and these are the data nodes and task trackers running over here, name node running your job tracker. Any questions till now? Sorry for that. So now when I say I want to process my file, or say I want to say count number of employees, simple query I ran on this data. Select count 1 from employees. That's all, simple query. So what this job tracker will do, it will check this data node, how much percentage of this data node is sorry, it will communicate with, it knows all the task trackers. This is your 1, this is your 2, this is your 3, 4, and your 5. Now these task trackers keep on sending their heartbeat signals to job tracker, so job tracker knows how much free these task trackers are, how much bandwidth they have to run a new job. Now say this is all red. This is all red. It's right now running some other jobs and it cannot do any other processing. This is partially red. It has some bandwidth and half red. So say 50% occupied. It is fully free. It's fully free. Sorry. Just a second. So task tracker 1 is all busy with doing some other processing. Task tracker 2 is 50% free, so it's 50% RAM is free, 50% CPU is free, and rest are occupied. And these are all free. So now job tracker knows the state of everyone because they are sending heartbeat signals to them. So now job tracker will see I have to assign your block 1 to block 4, and I can assign the task to these task trackers only. So it will based on the different criterias which are totally free, and the applications which are available, and how much process our task tracker can do. So it will assign the task. So say it has assigned for block 4 and block 1 to task tracker 5. I'll mark it as processing. So brown color is processing. So here and oops. And here it might assign for block 3 and remaining is your block 1. It might assign over remaining is your say block 2, so it might assign to block 2 over here also. So it will all depend on the job tracker. Now they will initiate a new JVM instance over here, will do the processing for these blocks and keep on sending the signal to job tracker that this much percent of the task is done. And once everything is done, they will just emit the data on the SDFS only. And the user can read the data, the output from the SDFS only. So when they emit on the output and on SDFS only, that will again be of kind of blocks and distributed on the whole SDFS file system. Now, does that make sense? Any questions now? So practically they would be emitting up, say count 4, count 5, and count say 7. And there's some other process which runs up our level. Don't worry about the complexity. Somehow that is sum to 4 plus 5 plus 7. So total employee count will 16. It will be emitted to SDFS. How that is done, don't worry. Well, I'll talk about that part in map and reducer. And when then the user just read it from the SDFS. So that will be a some block lying in say somewhere over here on this data node. Okay, so and one JVM for each block. Yes, one JVM instance for each block. So what is a new user is running? So Chris has another question. So what if a new user is running a new job? So what if a new user is running new job for the same file? So in that case, again, Chris, same thing will happen. The block 2 copy is lying over here also. So that might be assigned a new JVM or to T3 to trigger that block. So Chris has one more point. So now we have 3 JVMs running, one for block 2, one for block 3, one. No. Here for block 4 and block 1, there will be two different JVMs, two JVM instances. One for block 4 and one for block 1. They will not be running a single JVM for two blocks. And for each is definitely. When I have to process one block for one user, one JVM instance would be triggered up. Yes, simulation is done by the reducer, Puneet. I don't want to add that complexity right now. I will add that. I will talk about that sometime. Just give me a minute. Yes, simulation is done by the reducer, and I will not add that complexity right now. I'll slowly and slowly add the complexities. So any other question? Is it clear now? I want to quickly listen yes and no from everyone. Please ping me yes or no. If it's still not clear, please ping me no. I'll again repeat it. But this is this is a major this is a major thing which you should be understanding up to understand all the things which we'll be discussing on later on. So if it's still not clear, please let me know. I'll again repeat it. Okay. So I have so Padmani. Okay. Well, I'll slowly and slowly read the questions. Padmani, what is 16 and 14? 16 and 4. 16 and 4. Oh, okay. So, Padmani, I was just pointing out, say, but in this block, there were four employee records. Say in this block, there were 5 employee records, and the block 1 and block 4 had say total 7 employee records and total of 16 employee records. And that is the output of this query. Say that this was the logic which need to be triggered up. So that is what I've printed over there. So Puneet, where from 3.125 came up. So let's say the file size was 200 MB. So I just said 64 MB block size. So approximately 3.125 or 4 blocks. So it's clear to everyone. Chris, Padmini, Puneet, Sally, and Raj. I think not did not join till now. Okay. Okay. So yeah, one go ahead, Chris. Mm. Chris, I'll unmute you. You can just speak out. I think I might have missed your question. You can now you can just unmute yourself and yeah, you can speak.
Yeah. So if you go back to the previous spreadsheet,
Sure.
so my question is on if two users at the same time logged in and running their own jobs, the same query, let's say across two users, select count one from employees, and the job tracker assigned those two users into DD5. So now I have the block 4 and block 1 running 2 JVM for the first users. Would I be running another 2 JVM for the second user? So it would be 4 JVMs running on that node?
So Chris, that will depend on multiple factors. So let's say my data node configurations are say for say 8 GB RAM
Right.
to trigger your JVM. So I require some JV some instance some RAM to trigger my JVM instance. Now let's say I've configured my JVM instance minimum size would be or basically everything runs in a container. So container are given the
Right.
sizes. So say I
Right.
have defined say JVM instances would be of 4 GB. Okay, so in that case now this block now this data node is all red. So this guy has gone red. It cannot be.
Assume that there's no, everything is busy at that point. There's many users doing a lot of things in
Yeah,
there and
yeah.
everybody's
So
busy.
that's where the picture of queue comes in. So then
Okay.
that job would be added to a queue if all the guys are busy. But let's say this is only half full. This is again half full. This is again gone red because it is running one more instance, and this is already red. So still two blocks would be processed over here, and for two that will be later on picked from the queue once these guys are done their job.
Okay, but if that DD5 is not fully busy, let's say 50% busy with 2 JVM,
Yeah.
the job tracker could assign another. I just want
Yes.
to understand the
Yeah, yeah,
relationship
yeah.
between the,
So let's
yeah,
say, yeah, let's say JVM instance is 2 GB only. So here it's 6 GB. So now right now it's partially occupied, 8
right.
GB. So let's say it's little red, little red. So in that case now it still has a bandwidth of two more JVMs. So it can be given a task to for block 4, block 1 again, or someone else also could be given up. But the probability of this guy giving for the same block for where it's running up is less as compared, because in that case I might be
Yeah.
doing the read contentions on the file system.
Yeah, no, I totally understand that. I'm just trying to find out. So if you have 100 users running, you're saying that there are a specific number of maximum JVMs that can be run in every, like DD5, for example, in this case. But still, the relationship is 1 JVM per block per user per task. That's the relationship. Is that correct?
Sorry, I missed your question. Sorry. Can you please?
One JVM
Mhm,
per block
mhm.
per user.
1 JVM per block per per request.
User job
Per
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 request
user
per user,
per user task, job
per
task.
user test. Okay. That's what I wanted to
Yeah,
know. Okay. Thanks.
sure. So Puneet want the count should be same for all data nodes cause each. No, Puneet, it cannot be same. Now, although the data size is 64 MB, but the employee record might be say so. Employee table is something like this: employee name, employee department, and employee snap. So one employee has added a snap of 16 MB. Another employee has added a big snap of 32 MB, and fourth employee has added a small snap of 1 MB only. So a block might have only 3 records, a block might have 100 records, a block might have 1,000 records. That will not always be the same. Your data is always not of same size. Records are always of different size. Someone is calling me again and again. Just give me a sec. Let me tell him I'm in a meeting. Just give me a sec. Sorry, that was Raja calling up. He was not able to join the meeting and he was calling from last half an hour and I was just ignoring his calls. I did not look at that. So he had some difficulties joining in and he was just trying to figure out that. So any other questions anyone has? Okay, so I'll assume it's clear to everyone. Do anyone want to repeat it in 5 and 6 lines so that I'm also sure that you will have got it, because this is the heart of whole system, how the processing happens up, and this is the beauty of the system, how I achieve the multiple processing on the nodes only, and how I achieve basically processing of petabytes and terabytes of data across the cluster without requiring the vertical scaling in the cluster. Anyone want to repeat? Total silent. No one want to repeat? Puneet, Padmini, Chris, Ellie. Okay, sure. I'll assume it's clear to everyone. If you still has any questions, oh, Padmini said please repeat. Okay. So let me again quickly repeat up for you. So job tracker, I as a user submit the job to the job tracker. Job tracker gives a new job ID to me. I as a user, by that job ID, I track my whole job, and your job is placed into the job queue, which is displayed over here. That so whenever some data nodes are available in the cluster, job trackers picks up the jobs from the queues and assign the individual tasks for those from those jobs to the corresponding task tracker which are running on the data node. And each data node is running a task tracker. And these keep on sending the heartbeat signals to a job tracker, and job tracker picks jobs from the queues and assigns the task for those jobs to the task trackers, and the tasks are ran by your task trackers in the corresponding data nodes for the corresponding blocks which are lying on those data nodes. And to read it, the logic is always copied into SDFS only, and this logic, that is what I've displayed over here, job.xml and jar.xml. The default replication of this logic is 10 rather than 3. And can anyone answer why it's 10, not 3? The default replication factor of this thing is 10 and not 3. Any guesses why it's 10, not 3? The replication factor of this logic, what need to be triggered by the mapper reducer code, is 10 rather than 3. Although the data is replicated thrice, but the default replication factor of this logic is 10. Yes, redundancy of 10, yes, Shelly, but why it's 10? Why it's not default 3 only? No, Puneet, I'm not saying data is repeated 10 times or replicated 10 times. It's just the logic. The logic which, if you remember on this slide, I told I as a user, sorry, where has it gone? I as a user copies the resources which are required. That is the logic which is required to run on the data. So this logic which I copies on the SDFS file system is replicated by default 10 times rather than 3 times. The replication factor of data is 3. However, the replication factor of this logic which I've copied into SDFS is 10. Any guesses? No one guess? No guesses? Okay. So here you can see each task tracker. So say my file is I have to process data of say 5 petabytes. You can think of there would be millions of blocks which need to be processed up. And if say my cluster is a 1,000 node cluster, that logic need to be read from somewhere. And if the default replication of that logic is thrice only, there might be some data nodes which need to run that logic, and that logic need to be copied from some might be lying on some remote data nodes. So in that case, and that remote data node might be in the same rack, might be in a different rack, might be in a separate data center also. So to reduce or make the logic locally or almost as near as possible available for the data node to read it from the SDFS, because this logic need to be transferred over the network while your processing is happening up. So to reduce the time to copy that logic to the data node where it has to run, if we replicate it 10 times, the probability of that logic occurring or lying somewhere nearby on the same data node is high, and it's read from there, and the remote communications are reduced as much as possible. Does it make sense? Okay, so I'll go back to PDF. When I have to say select start from employees, what I'll do is I'll create a Java code for this query, and the Java code would be submitted to SDFS file system. So now let's say the Java code is called j.jar. This is a Java code which I've created out of this query. How that is done, don't worry about all those complexities. But somehow the Java code is created out of this query, and now this logic need to be read. So this logic, if you remember over here, that logic was copied onto SDFS. This logic was copied onto SDFS by your client or the user who has submitted the job. So this logic goes to your data node. So this logic size might be say few MBs only, few MB only. So this logic is available, say j.jar. One was copied over here, one was copied over here, and one was copied over here. If the replication factor was 3 only for the logic also. So in that case, when the logic is required on this data node, there's a data transfer which is happening across the network. And if say this data node is lying on some other rack, in that case, a rack transfer would happen. But to reduce those parts, this logic is basically replicated 10 times. So the transfers are less. Make sense? Is it clear to everyone now, or any other questions anyone has before I move it? So Chris, you want to repeat up the whole thing before I move it? Because I'm not listening yes and okay from the class much. Or Puneet, do you want to repeat? Okay, sure. So let's go ahead. So we talked about the job tracker. Job tracker really. Just a second. There's some problem with Raja is having in joining in. I'll just try to help him out. Hi Raja. Hello. Yeah Raja. What is the problem you're getting? Aren't you using the same link? Technical difficulties. Did you download the GoToMeeting software or something? So no, everyone else is in the class. I don't know what. Is your internet working properly? Okay, so let me again send you the link and try with that. I'm again sending you on your email ID, Gmail ID, which you have shared to me. I'm again emailing you. Just try that again. I don't know what is the problem you are facing because everyone else is in the class. or yeah, the session is recorded. You can view the recording session, but I'll again email you once again. Just give me a minute. I have your Gmail ID. Yeah, I have it from yesterday's session. Sure. Thank you. Guys, just give me a minute. He's having some problem joining in. Just give me a minute. Sorry for the trouble. So job tracker is the person who really track your whole life cycle of the job and do all the booking activities which are required to maintain the life cycle of the whole job and assign the task to the corresponding task trackers which are running on the data node where the real data is lying up. The task trackers run or trigger, spans multiple JVMs to trigger your map or reduce logic, and that JVMs really process your blocks of the file which are lying individually on the data nodes. And the job tracker fails to receive the heartbeat signal from the task tracker in the specified amount of time, the job tracker assumes the task tracker is down, and it will resubmit those tasks to some other data node. So where it has heard the healthy heartbeat signal. Yes, Puneet, he's trying to join from iPad only, but I don't know what is the problem which is facing. Heartbeats we have just talked about. Replication engine. So I'll again repeat the thing. The replication is by default 3 of the data, and if some data node, so these data nodes keep on sending heartbeat signals to name node. So if did name node did not heard a heartbeat signal from the data node, it assume the data node is down, and it will send a signal to some other data nodes to replicate those blocks which are lying locally over there on those data nodes. So this is how the write happens in the cluster. I, as a client, request the name node that I want to copy some file in the SDFS cluster. So I give a request to name node. Name node returns me where the on which data node the block need to be written up. Now it's my responsibility as a client to give a write signal to those data nodes to write the block. So I, as a client, will send a write signal to data node 1, which is written by the name node. That data node 1 will send a write signal to second data node, and that second data node will send a write signal to third data node. Third data node will send an acknowledgement to second. Second will send an acknowledgement to first. First will send an acknowledgement to client, and client will send an acknowledgement or complete request to the name node. And this is how the whole write happens up in the cluster. And this is the reason yesterday I told you people that the second and third copies are maintained on the same rack rather than copied on the third different rack, and that is because I reduced this network bandwidth, and I am also able to achieve the replication factor of 3 and good reliability in my cluster by copying the data on 2 different racks. So can anyone tell me what will happen if, say, while writing this data to this data node, at that time this data node goes down? So say this is 1, this is 2, and this is 3. So what will happen, say data node 1 is trying to write the block to data node 2, and at that time data node 2 goes down. What would happen? SDFS client is Hadoop component. Sally, when I'm saying SDFS client over here, I, as a user, submits a request of write. So there's the instance or SDFS instance, which is I communicate to the local SDFS instance on my data node, and so basically it's something like this. I as a user gives a write request, right? That write is communicated with the name node. Name node returns up. This write requires the block. So say this write has only one block for a time being. So that need to be written on data node 1, data node 5, and data node 6. So I as a client will give a instance or give a write signal to data node. And everything is done by the Hadoop cluster at the backend. You don't have to worry about those parts. I as a client will just give a signal, copy so and so file. But I as a client would be running up or setting up on some data node to communicate with the cluster or somewhere in the network. So here I am saying this client is sitting on the network. So this client would be our Java instance. The client would be something which is sending a write signal only. Hey Raja, are you there?
Um,
Yeah, go ahead.
so would I be writing the HDFS client and sending commands to add blocks to the name node?
Yes. So what is basically done is okay. So what is basically done is I communicate to Hadoop.
Okay, so that's where I
Yeah.
communicate to
Yeah.
Hadoop
So
and
Hadoop,
use
this is the
the
command which I'll type,
API.
communicate to Hadoop, and will give a write command.
Okay.
Right?
Okay.
Okay.
Okay. Thank you.
Sure. So this is how the data pipeline happens up. It copied from one. Okay. So, but I had a question over here. Can anyone answer what will happen if the data node 2 goes down while data node 1 is trying to write to data node 2? What could happen in this scenario? What should happen in this scenario basically? So by the time you
But
people
wouldn't a message be sent that it failed and then it would retry it with a different node?
Okay, so it would if I have to retry to some other node, some other data node, what will happen is this data node has to send a signal to the SDFS client. This will again communicate to data node, name node, and name node will return some other data node, and this will be a long, lengthy process which is required. So this is not happen. This does not happen in the cluster. So what happens is this data node, when we'll try to write to data node 2 and data node 2 is down, it will send a write signal to data node 3. And data node 3 will send an acknowledgement to data node 1. It will send an acknowledgement to HDFS client, and that will send an acknowledgement to name node. I'll change the color. Oops. And this will send an acknowledgement to name node. And now name node knows that the block was copied to data node 1 and data node 3 only, and for to data node 2 it failed. So at the back end, name node will maintain the replication factor. Later on, it might send a write signal to data node 1 or data node 3 to copy it to some other data node 4. So that name node will manage at the back end. So there's default write, successful write, which is again configured in the cluster. By default, that is 1. So even if the data is copied to one data node, the write is assumed to be successful, and the replication factor is at the back end maintained by the name node if there's a failure in the write process. So there's something called successful write, which is default configured as 1. So even if the data is copied to one data node, that acknowledgement is sent to the name node, and in such a scenario, name node at the backend transparently to us maintains the copy by communicating to that data node where the blocks are copied and asking them to write to some other third data node, which are up and alive. Chris has a question, does all the nodes aware of the other nodes? No, none of the node is aware of any other node. It's the name node only which is aware of what is going on the nodes and where are the nodes. And when this write signal is given up, it has information which data nodes this block need to be copied up. So in such a scenario, these data nodes communicate to each other. In any other scenario, they do not communicate to each other. So Puneet has a question. So 3 copies will be there, right? Yeah, definitely. If in this scenario the 3 copies are not somehow were not done because these data nodes were down, at the back end, transparently name node does it. So in now if the data node 2 was down, it will later on name node will send a signal to either 1 or 3 to copy it to name data node 4. Chris, how does the node write? Sorry, Chris, how does the node write to 3 instead of 2? Because this, when a write signal is given to this data node, it's not only the write signal which is given, the write signal as well as the write signal to two other nodes only. The data node 1, data node 2, and data node 3. And where it's said the second write will happen to 2 and third write will happen to 3. So it knows the second write will happen to 2, it will communicate to 2. But when it's trying to communicate to 2, it's not able to communicate, it's not able to ping to 2. So in such a scenario, it will try to communicate to 3 and will send a write signal to 3. So it's not only the data, but the path of the network is also given with the data. That's how this data node will know where to copy it, and this data node will know where to copy it. Make sense? Yeah, definitely. It's a part of write request. Raja, are you in now? Can you hear us now? Looks like he's having some difficulty. Okay. So this is what I discussed in the previous slide. This is called data pipelining or write pipeline in the cluster. And the read are pretty simple. When I as a client has to read something, I just communicate to the name node where the file is lying, which are the blocks associated to the file. Name node returns me the location of the blocks, and when it returns me the location of the blocks, it always try to figure out or find out the nearest blocks to me. So when I'm saying I as a client, I might also be sitting on somewhere on the network, say on some data node, say on data node 1, and if some blocks are lying locally over there, name node will always try to return the location of those blocks on the same node only. So I get the location of the blocks, and the nearest is taken care by the name node, and I read those blocks from there. So read is pretty simple. So there are also at the backend data corrections, data checksums which runs at the backend. So okay, so what happens is say my file was divided into 5 blocks: block 1, block 2, block 3, and so on. And when this data is copied with the block, there's some headers also with the block, and these headers have some algorithms on the data. So there's some checksums which are generated on the data, and these checksums are continuously monitored so that and there's a backend process which runs up, which do the validation of these checksums. The algorithm uses CRC32 checksum algorithm, and if it finds that some data has got corrupted, that is communicated to name node, and name node in that case creates a good copy from some other data nodes where the good copy of that block is lying up, and this is how the healthy cluster is maintained at the backend. Any questions from this whole PPT, what we discussed from today, yesterday? Any questions, any doubts, anything? Sorry, Chris, I am not able to get your point. What do you mean by same with reads? Okay. So we'll move on to MapReduce, but before that, let's quickly recall what we discussed over here. So I'll ask questions and I request you to go ahead and answer them. So what is job tracker?
Job tracker tracks all of the, it communicates with the task trackers on the different nodes. It's on the name node, and it's basically the brains of deciding which node is going to be working on which different data.
Yes. So basically, it do all the bookkeeping activities required for your whole job to be run up.
Right.
So next question. So I want someone else now to answer. What is task tracker? Padmini, you were very much quiet. Do you want to go? Do you want to answer?
Yeah, task tracker is nothing but like in order to pick up the data, right? The job tracker assigns the particular job to the task tracker, and indeed the task tracker go into the block and then picks up the data which has to be read, and then gives back the data to the job tracker, and then that's how the job is viewed.
Let me correct few points. So there's never a data transfer happens between job tracker and task tracker. This is a communication only which happens up. So the data is
Okay,
lying. Data is always lying on the node where the task tracker is running up. And task tracker just initiate a new process which reads the data, process the data, and again put that data into SDFS.
okay.
Okay. So okay, and the data or the logic which is copied in the SDFS only, and that's read from the SDFS only. And why that logic is replicated highly as compared to data? The replication factor of that is 10. However, the data is 3. Puneet, do you want to go ahead for that?
Yeah. Am I audible?
Yeah, you are.
Yeah. Okay. So because there are a lot of chances that if any job fails, then the probability would be quite high if there are a lot of logics copied on different nodes. So in order to reduce network bandwidth, there are a lot of logics. I mean, logic is copied on greater number of nodes.
Yeah, but that is not related to failing up. Padmini, actually, whenever you are on mute, there's a lot of echo. I just request you to put. Yeah, thank you. So, what I was saying. So that no, that's not related to failure. That's related to because that task need to be initiated on n number of data nodes. So the tasks should be available as much locally or as much near to the nodes where that logic need to be ran up. So that logic is highly copied with a high replication factor.
Okay.
And so Chris has the one more question. Reduce. Yeah. That's the correct answer. Yes, Chris. Okay. So just give me a minute. Let me open another PPT of MapReduce. By that time, if you have any other questions, you can just recall up and ask me. And just give me a minute. Let me open another PPT. So I've completed this whole PPT, Hadoop basics, and I'll be sharing this PPT on the drive with you. And okay, so I've started advanced MapReduce. Okay. Before I go over there, let me show you a few more things. I hope my screen is visible to everyone. Yeah. So I'll just move on to MapReduce part and the other things. But before that, I'll be sharing all these things with you. You can just download these things on your laptops because these are heavy software. over the whole week, and we'll be discussing. I'll be helping you and telling you how to install them, how to use them. Don't worry about that part, but just copy them or download them on your laptops so that you can use them in the next classes. I'll help you how to install them. Don't worry about the complexity of installing and what to do with them, but just download them. I'll be sharing that thing with you. So I'll be sharing this whole Hadoop software folder with you, and this has a lot of things. Don't worry what these things are. I'll explain you all these things. So it has Eclipse, it has Java, it has all the code which we'll be discussing in different classes. It has your virtual VMs and everything. So I'll help you. I'll tell you what are all these things in our next class and how to install them. And you can do it, but over the week you can just download them because this is all 4 or 5 GB stuff. So I'll be sharing this whole software folder with you on your Gmail ID, which is shared to me, and you can just download it. And then I'll be putting up the PPTs in this folder as soon as we are completing up the topic. So you can always go to this folder and read them. I'll be sharing this folder again with you, people. And whenever we'll be doing up the exercises, I'll be sharing the exercises with you. So right now I'll not be sharing any exercise folder with you. Okay, so before going to MapReduce, let me just quickly show you a glimpse of how the things look like, how the Hadoop looks like, and what we do when I was talking about job tracker, task tracker, and the read and write anatomy. Let me quickly show you how everything happens at the back end, and then we'll switch over to MapReduce. Okay, so what I'll be sharing with you is a virtualized environment. Don't worry about that part. I'll talk everything how to install these things. But let me just quickly show you. So this is a virtualized environment where all the Hadoop related softwares are integrated in this VM. This is shared with you. I'll help you how to install it, how to configure it in the next class. And I'm just trying to start it up, and we'll try to communicate with it and fire some commands how to communicate with it before going to the MapReduce part. And we'll just try to read something and write something in HDFS and show you some of the HDFS command how to interact with it before going to MapReduce part. So it will just take a minute or so to start up. Okay, by the time it's starting up, let me tell you the softwares which are there. Okay, so now I've logged into that VM, which I've just now started on my PC. So this VM is a virtualized Hadoop cluster, single node cluster, which is enabled on my PC right now. I'll tell you how to do that. But this whole single node cluster is enabled on my laptop. When I'm saying single node, there's only one node which is running your data node also, which is running your name node also. We are using a single node cluster because if you run 10 nodes on your laptop might not suffice that much kind of memory, and so this is an environment virtualized for you to do your development stuff. How we are interacting with the system will remain same whatsoever the side of a cluster. You might be logging to any of the data node on your cluster and will be writing these commands. So right now I have logged into the node which right now we started up, and I'm trying to interact with the Hadoop cluster. So to interact with the Hadoop, we write Hadoop fs. So Hadoop fs is a command to interact with the Hadoop file system. So I say Hadoop fs and press enter. It will tell me different options how to communicate up. So let's try to run something. Hadoop fs minus ls at the root. So now it's tell me all the folders which are lying in HDFS file system on root. So it's all everyone knows Unix commands, little shell commands, ls, copy, f, cp, mv, put. Is there anyone who does not knows the normal Unix commands? Just normal one, MV, copy, put, CD, these kind of things, right? Everyone knows it. Okay, okay. So same applies over here. All you have to do is just type Hadoop fs, and the similar command would be here. So minus and the command. So cp is there, ls is there, mv is there, mkdir is there, and but when I'm saying Hadoop, when I'm prefixing that with Hadoop fs, I'm interacting with Hadoop file system. So Hadoop fs minus ls and root, it displayed me all the directories lying in Hadoop file system at root. So Hadoop fs minus ls slash temp will display all the files lying in this folder. By mistake, I've copied 2 slashes. So we'll try to put some file now and try to read some file over from there. So say there are a lot of files lying over there. So let's try to read this file. So what I have to do to read this file is Hadoop fs minus, if I have to just read it, cat or something similar to that, cat or tail, cat, and this. So this now this file will be printed on the console. Now by the time file is printing up, I want someone to explain me what is happening at the backend. While the system is getting the file over here, I want someone of you to go ahead and explain me what happened at the backend.
So isn't the what it's going through and it's collecting the different blocks from the different data nodes and assembling them and getting the data back from the different nodes? Is that right?
Yes, yes. So
Okay.
at the backend, practically you won't be reading the whole file. So this is a thing which you practically will not be doing the cluster, but definitely
Right.
this is what happened at the backend. It communicated with all the data nodes in the cluster, collected blocks, ordered them over here, and printed it over here. Padmani says,
But is it sending it?
uh,
You're not getting all the data, are you? You're just getting. I
so
mean, on a real system, you wouldn't
so
do this.
yeah, yes, yes, Ali. On the real system, you won't be printing 5 petabytes of data on the console.
Right.
Yes.
Okay.
So you might be just reading some part of the file or doing something related to that if you have to read it. Or practically you would be sending your code to process the file.
Okay.
Yes. So that, but I just wanted to tell you what is happening at the backend. These clients are automatically triggered. Hadoop FS will create that client. That was the question, right? What is the client? So this Hadoop FS will create a client, file system client that will do a communication with the file system and will do the things for you. Yeah, Padmani, I'll just read your question. Any OS restrictions to install the software? My laptop has Windows 8.1. Yeah, definitely. Windows 8.1 is fair enough to install all these things. Is there anyone who has a laptop less than 4 GB RAM? Yeah, Chris, Mac OS will work. I hope all of you has laptops at least 4 GB RAM, right? If it's less than 4 GB, it will be difficult for you to work, because this VM really requires is a kind of RAM crazy. So sure. Okay. So Hadoop FS minus. Okay. Before that, let's look at some files lying over here. So there's a file lying MSK file SDK. So Hadoop FS minus put. Now I'm trying to put this file from my local. I'm again repeating, from my local Unix box to SDFS. So here I did a ls, that was my local Unix box. I'm trying to put this file from my local Unix box to SDFS. So I'm saying Hadoop fs minus put and this file and to say /temp. So now this file is copied from my local PC to SDFS. Now I want someone else to explain me what happened at the backend. So this file is copied to temp. So by the time I'm looking, doing ls on the temp, I want someone of you to just quickly talk about what happened at the backend. So you can see what was the file name I copied? Mike. So here it is. So this file is copied to the temp in HDFS. So Hadoop fs minus put did all that right logic what I was talking in the previous slides. And similarly, I can say Hadoop. So if you don't remember all these things, all you have to do is Hadoop fs and press enter. This will give you all the help what is related to fs. So tail is there, text is there, copy is there, account is there, copy from local. Copy from local is same as put what I did right now. And copy to local is same as get so Hadoop. Sometime you might require this Hadoop fs minus get or copy to local. And let's say I want to copy this file over here only. So now the read is happening. I'm copying the whole dump from HDFS to local Unix box. So if I say ls, is the file there somewhere?
So
Yeah, it is there. Yeah, go ahead, Chris.
So quick question there.
Yeah.
So when you do the fs or Hadoop fs dash ls, that list of files, is that coming from the name
Yes.
node by itself?
That's what I wanted you to answer. Yes, that's what my question only. So it communicate to the name node. Name node returns the metadata. What is the metadata? It's just the metadata which is written from the name node and displayed over here. There's no communication to any data node.
And once you start doing the actual read, that's when the client will go to the actual node provided by the name.
Yes.
And to do the read.
Yes. So I'll again repeat what Chris said, and that is what I wanted you to answer up. So when I said Hadoop fs minus ls, there is no communication to any data node in this command. But when I said Hadoop fs minus cat temp slash what was that file? Now there's a communication with the name node as well as data nodes, which are containing blocks of this file. Okay, so Hadoop fs is a command how you interact with the Hadoop file system. Go ahead.
So when you do the ls, it's just communicating with the name node and not the data node.
Yes, it does not require to communicate to data nodes.
Okay, because that's just keeping a record of what the files are in the HDF file system, and so it can just give you that ls response back. But once you want the content, then you need to interact with the data node.
And indeed, data node itself does not know what the data is. It just stores the blocks. Data node practically does not know what that is. Yeah, so that is all known by name.
Oh, that's true.
Yeah.
Okay. Thanks.
So Puneet, how to check the blocks of a single file in the data node? In the data nodes, how to check the blocks of a single file in data nodes? So there are commands related to admin SD. HDFS data node, and the data node name will do a data node checkup and will return you the blocks over there and things like that. So if you look at HDFS in detail, this will help you to do that admin related stuff. For what are the blocks lying in a data node? What is the status over there? If I have to do some checksum, all of these things are there. Okay, so
is that most of the administration of it?
Yeah, that is the administration part. So that's why.
If you were doing HDFS.
Yeah, SDFS.
Okay.
Yeah, SDFS. Yeah. So this SDFS is all related to administration. Hadoop, what I was triggered previously. So if what I did, what I printed, what I printed. Oh, okay. Data node and then so this printed all the data nodes what is running up and that did all else. So whenever you have to look for any help on any command, just type Hadoop. This will give you all the options related to Hadoop. So FS is one option which we was using right now. There are other options also. We'll look at them. And if you have to look at Hadoop FS enter, this will give you all the options related to FS, SDFS. It will give you all the options related to SDFS data node. Say it will give you all the options related to it. So right now it's trying to communicate with the data node. It requires the parameters. So that did that and then printed it over here. So you can always look at the help of any. Sorry, Puneet, sure,
No,
please
it's
go ahead.
Chris.
You can go ahead.
Yeah, my question is, so everything Hadoop deal with is a file based. There is no concept of the relational database part of Hadoop. If I have a relational database
Yeah.
Hadoop, do I have to export it separately as a file?
Yes. So we started in 90s, 1920s and 1950s with the file-based systems. Oracle and relational file systems comes up. File-based systems gone vanished away. Again, we are moving to the file-based systems. Hadoop stores everything in file system only. There's nothing related, nothing like what you're talking about. Everything is stored in files, and we read the files. We do the processing on the files. So we print the output of the process data. Everything in file system only. We are again moving to the back old days systems.
So when you do a select statement like you did before, select and do joins, are you actually executing a select statement? Does Hadoop provide the APIs for you to deal with it as a database?
Okay. So I'll not go into the complexity of our question right now, although when we're covering Hive, that will be very much clear to you. But to explain, to answer your question, we define metadata on the files. So what we do is, so let's say this was my employee table. I did a select from this table. So let's say this was the employee table which had employee name, uh, employee DPT department, and employee snap. So these are the three columns in my table. Okay. So at the backend, this data would be stored, say, comma separated. My file is say comma separated. So that will contain Chris, say anything. So this data would be at the backend comma separated. So I'll tell, or I'll basically add the metadata with this file that knows the data is comma separated, and the second place is the second place is the department, first place is the name, and third place is your snap. So when I say select count star, my logic would be in such a fashion that it will read this data with the metadata of the data and will do the processing for you. Does that make sense a little bit? How that metadata is created, how everything happens at the backend. Everything happens transparently to your backend. You don't have to worry or write any code for that. That is done with the beauty of Hive. I'll explain everything in detail, but does that answer your question a little bit?
Yes, it does.
Okay, so Puneet, that is the question. If I am reading a file from SDFS, it is automatically combines all the blocks associated to yes. So everything happens at the backend with the communication with the name node, Puneet. If I'm reading a practically in my practical scenario, I'll not be reading the whole file. Does not make sense. But even if I'm reading it, yeah, everything is will be done with the virtue of name node and the communication with the name node. Okay, so Hadoop FS is the command which I was telling you, and let's go back to the PPT. So this is what is displayed over here also, Hadoop FS and different commands which we just now did it. -rm is the remove command. So if you have to delete some data, you can use -rm. And if you want to delete recursively, you can use -rm -r. So that will delete the recursively, or -rmr. So both will work. Minus, oops, -r m r or -r and -r. Both will work. Recursive delete. And put get, we just see ls are recursive list. ls mkdir, you can create a directory mkdir and things like that. So this is a one way how I can interact with the Hadoop based file system by using Hadoop fs command. The another way is writing Java code. So don't worry about the Java complexity for those who don't know the Java code, don't know Java. Uh, Frankly speaking, practically speaking, even though people who have a Java background will not be using this Java code to interact with the file system, they would be using either HDFS or Hue UI. I'll show you in some time to interact with the file system. But I'll just telling you for your benefit because you are joining this training course, so you might be knowing it. You might require at some instance in future, but I am damn sure that you will never be using this code to interact with the file system Java code. But just for your benefit, I'm showing you this code. So for those who do not have a Java background, you can ask me up any questions which you have, but you practically will not be using this code to interact with. You might be using the Hue UI or Hadoop commands to interact. You won't be writing such a big code just to read a file when that could be done with from the Hadoop fs command and with Hive and Pig. So to interact with the file system, all you have to do is create a configuration, that is configuration, new configuration, and there you can just say get. So that will return you a configuration of Hadoop file system. And if you say get local, that will return you a local file system, that is a Unix box configuration. So I'll be using these file system objects to interact with the file system. And this is a package which you would be using up to interact with the Hadoop file system from Java. So again, for people who are not from the Java background, Puneet, Padmini, Chris, I'm not sure. So yesterday you did not introduce yourself. So Chris, also you can you introduce yourself? I do not know anything about yours, you, and anyone does not know because you were, I think, on mute yesterday. Chris, are you there? Could you just brief me about yourself, your background, your profile?
Yeah.
Okay.
Can you hear me?
Yes, I can hear you now.
Yeah. I'm a chief architect at Cognizant right now. I do a lot of architecture design. I am from a Java, C, and C++ background. Unix, Windows, .NET, worked on all these three platforms. So it's really mostly, I do a lot of integrations, a lot of architecture, a lot of business process management type of software. That's my background.
Okay, sure. That sound good. Sure. So, Padmani, Puneet, don't worry about the complexity of the Java code. You practically won't be using it, but I'm just trying to explain you how you interact by Java to HDFS file system. So you can use this package. When I'm saying packages, all the Java code is always, zipped up, or what we call jar in Java world. And these packages or these class files are zipped in that. So these package you can use this package and get a file system object. And with the help of file system object, you can interact with the file system. So it's very, very easy. Once you get the object, I've got the local object, I've got the HDFS file system object. Here I am just saying list all the directories locally. So in this program, what I'm doing is, before I tell you what I'm doing in this program, I have a question to everyone in the class. Hadoop file system says, rather than putting up smaller size files or say hundreds of smaller files, put a big file. So rather than putting 1 MB 100 files, keep a 100 MB file. Can anyone guess what is the reason behind that? Why Hadoop file system says or prefers to have bigger files rather than smaller files, files of smaller sizes?
Because they're already breaking up to smaller pieces with the file blocks, so it controls that breakout instead of the user specifying the smaller size.
Okay. Actually, even if you have, so right now I gave an example of 1 MB file, but let's say Hadoop file system says rather than having 100 MB file size of 100 MB and 5,000 such files, put a single file of 5 petabytes. So, but my objective of saying is it does not, supports or do not, what is the right word I should say, do not encourages you to have smaller size files. And Chris, I do not buy your point fully. Basically, the reason is if I have a lot of smaller files, the name node bandwidth or name node storage is occupied in maintaining that metadata. So to make or to keep your name node free as much as possible, it's always encouraged to have bigger size files rather than smaller size files. If I have a single file, the metadata which is maintained by the name node would be less. And that's the reason behind that. So over here, what I'm doing is I have written a Java code which is reading a lot of smaller files from the input directory or from a local file system and combining that to a single file and putting into HDFS. So what I'm doing is I am reading all the files from a local file system, what is the input to this program, and I've created a new file in HDFS file system, hdfs.create. So HDFS was an object to HDFS file system, local is an object to local file system. And here I'm looping all the files in my local directory. I am writing, so I'm reading that bytes by bytes and printing that byte to the output, which is nothing but the HDFS output. So this output stream is an HDFS output stream. Is the output stream and HDFS output stream. I'm reading bytes by byte from the local file system from all the files which are lying in my local file system, combining that to a single file and dumping it to HDFS file system. That's pretty simple Java code where I'm reading up and writing up to HDFS file, where I'm reading from local and writing to HDFS file system. So this is how you can communicate with the HDFS file system from Java code. I'll tell you how to run this Java code, but I'll not tell in this class because most of you are not on your laptops. So I'll tell in the next class how to run it, how to use the Java code to interact with the file system. But okay, let me run it locally on my PC at least. So that will give a little glimpse how to communicate. So this file is already lying up. I've already created a jar. How jar is created, don't worry about that, but I'll explain everything to you in the next class when you have your laptops and downloaded all this code. So cd dot cd. Okay, so here is my file line.
So when you say just quickly, when you say next class, is that a different class than this one?
Next class, I mean to say in the next section. So the classes will be on every Saturday and Sunday for next 5 to 6 weeks. So when I'm saying next class, that is the next Saturday class.
Oh, so next Saturday and Sunday, we could join in the same time and the same link and all that stuff.
Yes. So the same link would be working up for you for next 5 weeks or 6 weeks till we don't cover the whole course, till we don't complete the whole course.
I see. Okay.
So Hadoop jar name is basically this jar has the code to interact with the file system, and then I can just give the class name and run that thing. So I'll explain all this thing to you in the next class when you have downloaded everything, so that you can reply, you can recognize the things. But this is how I'll be triggering that Java file to read it. The third way to interact with the Hadoop file system is the Hue UI. So that is a beautiful UI which you can use up to interact with the file system. So this is a URL which you would be using up. Once you install everything, I'll give you all this UI and the password, how to interact with it. So in the next class, you just download everything, and I'll tell you how to install it and how to make up this Hue UI, how to interact, how to open this black box which I was showing you, and how to look at this screen, how I ran it. I'll explain you everything in the next class. So this is the third way how I can interact with the Hadoop file system. It's a Hue UI. which is again configured on already configured and in the VM which I've shared with you. So this is a file browser over here. This will display the file system onto you on the UI. So if I go to root, so it's displaying all the directories in the root and SDFS file system. So this is the temp directory. If you can recall, in the temp directory there was one file which we copied. There's a file displayed over here. So now again the communication is happening with the name node and the data is displayed over here. I can also do a lot of things on this UI. I can copy the files directly with the help of this UI from a local Windows laptop directly to SDFS. I can download the SDFS files directly from the SDFS file system to my local Windows laptop and things like that. I can even open a small, if the file size is small, it will open it over here also. So if this file is small, it will open it here only. If I click on this file, it has opened the file because the file was small. And say it says first block, next block, next block. So if file was segregated across the blocks I would be able to see the blocks also. And if I click on edit file, I can edit the file locally over here. So over here, the communication happening with your Hadoop cluster. The data is getting transferred over the network to this UI, and that is displayed over here. I can even upload the files directly from my local file system to SDFS file system over here. So there's an upload button. I say upload files. It says me to select the file. Select the file locally from my local Windows. So I selected the file. Says open. That file is now copied. Now everything happened at the backend. Communication with a name node, blocks, or everything happened at the backend. The file is copied into your SDFS file system. I can even download some file. I can click on it and say download. So I can download it directly to my local laptop. I can even change the file permissions from here directly. So similar to your Unix file system, your files in the SDFS also have the similar permission level things. So you can give the permissions to your file. You can change the permissions to a file. They are root users, they are users, and I'll talk about them. You can copy the files from one directory to other. You can move the files. You can do everything. You can rename the files from this UI. So if you can recall in the start of the course, I told you we'll be talking about Hive, we will be talking about Pig, we'll be talking about different things. So all those things you can write those commands over here. Hive command, Pig command. I'll be talking all those things as soon as we will be proceeding up. I can view the jobs running in my cluster. So right now there's nothing running up. Let me try to run up something. So I'm just trying to run some job, submit some job, and then we'll be able to view that job over there. So don't worry what I'm typing right now. I'll explain you all these things in Hive class. But I'm just trying to trigger some job. So Chris, right now the file is lying over there. The metadata is defined on the file, and I'm trying to interact with that file with a normal select command. So Puneet, I'll just read your question. I can see it, but I'll just read it in a minute. So let's say some job would be triggered up. Oh, still that is happening up. So that job submission and everything is happening up at the backend. Now the job can be tracked over here. So see, the job is there, and I can see the whole job state. I can even go inside the job, look at different things about the job. So this is a direct URL application URL. Oops. What happened? So see, that job has that job is running up. That job is creating one mapper, so that there's a communication happening to a task tracker where this mapper is, or the data was lying up, and it will show you all the status about the job. So I'll be explaining all these things to you, but I just wanted to give you a glimpse so that you can think over the whole week about all these things. So the job has ran, and I can check on the Hue UI, which I was showing to you. Job tracker, so that job has succeeded up. So here the communication is happening with your job tracker to display the different jobs which are running up, the status of them. So when here the status is coming up, combined up from all the individual task trackers. So Puneet has a question, can I upload my Windows file into HDFS using PuTTY? Yes, Puneet, you can do it. From PuTTY, no. PuTTY does not support FTP protocol. So you require something with FTP protocol. I've shared a WinSCP over there in the softwares folder. By the help of that, you can do it. I'll explain those things to you in the next class. But PuTTY does not support FTP protocol, so you can't upload your file from Windows using PuTTY.
So the link. Just a quick question there. I didn't get a chance to open the link that you sent. The link that you sent has all the Word file for all that stuff in one place that I could download and install.
Okay. So I'll be sharing that thing. I have not yet shared it with you. Yeah, all the software which are required for installation, that will be in a single folder. You can download the whole folder as a zip. So you can download this.
And you already shared.
You can download this whole
Oh,
software
sorry,
folder as a zip.
Oh, you already shared that link to this folder?
No, I'll just share it. So yesterday I got your Gmail IDs. I've written that. Let me share it right away.
Yeah, I wasn't sure.
So you people can.
That's going to give you the Hive, job browser, and all that stuff.
Yeah, it has everything. How to install them, how to use them. Don't worry about that part. I'll explain you in the next class. So, but whatsoever I was showing right now, everything is there. You just download those part. I'll explain you how to install it. So next class, I'll be telling you. At the time you can try installing them.
Okay.
Okay. So I've shared this whole folder with everyone, and I'll share the PPTs also. So I'll share the folder, but I'll keep on copying the PPTs over there. Okay, so we are running out of time. So any questions over here? So this is how you can interact with the Java. I'll run this program also in the next class to you. Once I'll show you the Eclipse and other thing. So before that, I wanted to people to show you the Eclipse and the Java code in the Eclipse and how to create the jar and how to put it over there. So I wanted to show you those steps before running this. That's the reason I'm not running the Java code right now to read the data. And then we'll be looking onto MapReduce part. Any questions? Anything which you want to ask up before we wind up for the day? Thanks, Sally. Thanks, Puneet. So you people can just download the software folder, which request would be there in your Gmail IDs. Just download the whole software folder. That might be 510 GB, I think 4 or 5 GBs. I'll explain you everything, how to do everything in the next session. Thanks everyone for your time, and let's meet over the next weekend and have a nice week ahead. Yeah, Chris and everyone, the timings, the link will remain same. Join on the same time on the same link, and we'll meet at the same time at your corresponding time zones. Nothing will change until unless communicated in advance to you. So if there's any change in the class or any change in the link, that will be communicated to you prior over the emails on your registered email IDs with us. Sure. Okay then. Thanks everyone. Let's meet at the same time next weekend. By the time, good afternoon and good evening to everyone, and good night. Have a nice day.
Thanks.
Sure. Thank you. Bye bye.